It's a pleasure to be here. Some of the things I'll be talking about today is joint work with Ian Leary. And if at any point during the talk you have any questions or want something clarifying, feel free to interrupt. Okay, so Mike defined for us what a polyhedral product is, so I can go ahead and construct one. So let's start off by considering the polyhedral product, where we take a circle and a point. And today I'm going to insist that the simplicial complexes that we use to build this will be flag. So just a quick reminder, this means that if you see the one skeleton of a simplex, you should see the whole simplex. So you see a triangle, it shouldn't be an empty triangle. This triangle should be filled in. Okay. And so, for example, if we just take L to be a line segment, then this is going to give us a torus. Okay, so I guess in the last talk, we had notation S of L being the simplices of L, but here I'm going to denote S of L to be this specific polyhedral product. So apologies for the confusion. Mike and I didn't confer on notes before our talks. Maybe we should have.
The script is.
So yeah, one of the reasons why I call this S of K is that sometimes this is referred to as a Salvetti complex. And something to note here is that one of the reasons why we need the input flag complex is that if it's not flagged, then we don't always have that this space is acyclic. And so it follows that this space is acyclic, so its universal cover is contractible. So in particular, it's a classifying space for its fundamental group. So as a counterexample, if we start with the triangle that's not filled in, or this one-dimensional triangle, then the universal cover of the space will look like lots of empty cubes, and that's not contractible. Okay. So what do we actually have here? We actually have right-angled Artin groups. So it turns out that the fundamental group of this polyhedral product that we defined, known as a right-angled Artin group. I'm sure many of you have seen these before, but just for the sake of completeness, here's a presentation. So you can define these in terms of both a graph or a flag simplicial complex. Because if you take a flag simplicial complex, you can just look at its one skeleton, or conversely, if you have a graph, then you can do its flag completion. So wherever you see the one skeleton of a simplex, just insert that simplex. Okay, and so the generators of this group are simply vertices of your graph, and the relations are commutators for every edge between two generators. And so some basic examples include free abelian groups. If we have complete graphs, then that just simply means that every generator will commute with every other generator, so that gives a free abelian group. Or if we have an empty graph, so just some set of disconnected vertices, then we just have the generators. We have no relations. That gives a free group. Okay, so and then in the notation, we can write either A sub L or A sub gamma. You know these. Okay. So some of the reasons why these are important, and in this section, this is really just going to be a brief glance because I only have half an hour, so I can't really go into all the technicalities of this. But one of the reasons why right-angled Artin groups are very important in geometric group theory is notion of cube complex. So a cube complex, roughly speaking, is a CW complex where the cells are cubes, Euclidean cubes, so direct products of unit intervals, for example. And we insist that the attaching maps are combinatorial isometries on the faces. So to give a non-example, something like square, so this is fine, this is a Euclidean cube. But then if we try and attach another cube like this wouldn't be a cube complex, because this isn't a combinatorial isometry on the faces. We really want two cubes that are two squares that are glued along an edge to really have the endpoints of the edges match up as well. This. And this polyhedral product as well that we defined turns out also has a structure of a cube complex. And in 2008, Haglund and Wise introduced a special notion of cube complex. So they gave some conditions that if a cube complex satisfies, then it turns out that its fundamental group will actually embed into a RAG. And this gives the group a lot of desirable properties. So subgroups of right-angled Artin groups are residually finite, linear, virtually torsion-free. And the conditions that they gave are fairly easy to check if you know your cube complex. So they consist of avoiding certain pathological behavior. And this had a lot of important impact. So one of the major examples of this was this led to the resolution of the virtual Haken conjecture. And so this was proved by Agel in 2012. And one of the main consequences of this is that if you have a finite volume hyperbolic 3 manifold, then it's virtually fibered. So let me say a few more things about that. So one way of constructing 3 manifolds is if you have a surface you start with, and you have some map F from the surface to itself. What you can do is you can try and construct the mapping torus of this. It will be the surface cross an interval modulo by F, and this gives you some 3-dimensional structure, and this will be a 3 manifold. So this is one source of constructing 3 manifolds. And what Agel proved was that if you have hyperbolic 3 manifold, it turns out that this is essentially the only way you can get 3 manifolds up to finite covers. This was a really big theorem with lots of important consequences. But the relevance of cube complexes was that in order to prove this, right-angled Artin groups were used in this way, that these manifolds were cubulated, and then you could show that actually they satisfy the conditions of Haglund and Wise, and it follows that these groups have very nice properties. So they're linear, and so on and so forth. That question?
Proving the virtual Hawking conjecture was, I mean, maybe virtually fibered does prove it's virtually Hawking, but I think they had, they always had something else in mind.
Yeah, so there were like I think at least 3 different questions relating to 3 manifolds. This was just the one I thought I could quickly draw on the board, but yeah, the virtual Hawking conjecture is slightly different. It's about maps on fundamental groups. Okay, moving on. So we're starting to get towards Bestvina-Brady groups now. So first, let me define almost finally presented groups. So say that a group G is almost finally presented, or another name for this is of type FP2. Sometimes you want to specify a ring as well, because usually type FP2 is defined in terms of projective resolutions, and there it's important what the ring is. But if you take the ring to just be the integers, you can just say type FP2 or almost finally presented. And I tried very hard to find a definition that didn't use projective resolutions or the group ring. And well, I'll let you be the judge to see if I've succeeded or not. We can try and look at it from a point of view of a short exact sequence. So we say our group G is almost finally presented if it can fit into such a short exact sequence where the middle term H is actually finally presented, and the kernel N must be perfect. So it must have trivial abelianization. So this means that the derived subgroup or the commutator subgroup of N must be isomorphic to N itself. So when you quotient by it to take the abelianization, you just get the trivial group. So I guess secretly here there is a homological condition, and n being perfect is the same as the first homology of n vanishing, but it's kind of buried here by just saying, oh, if this group is perfect, then we have what we want. Okay, so this is one definition of B being form is finally presented, and finally presented groups are examples of this, because we can just take n to be the trivial group. That certainly has trivial abelianization, and we can take H to be G itself when G is finally presented, and so that map between H and G will just be an isomorphism. And so these groups AL, the right-angled Argand groups that we define, as long as we start with a finite simplified complex L, this will give us a finite presentation. Okay, so then it was a big question for a while whether there exist any groups which are of type FP2 but not finally presented. I think there were some people that believe that maybe these notions are so close that maybe they coincide. And before I say any more about that, I should probably mention that, yeah, there are lots of cases in which they are the same. And so there was a recent result of Marco Linton, who proved that for subgroups of one related groups, these two notions do in fact coincide. And there are many other occasions where these notions do coincide. But this was a recent breakthrough, which was important because together with Achaiki and Sapiran and Linton, they managed to prove that one related groups are actually coherent. So first they showed that finitely generated subgroups of one related groups of type FP2. And then because Linton was able to show that FP2 is the same as finitely presented, but in fact, finitely generated subgroups of one related groups are finitely presented. So this is like one of those cases where this question has a positive answer. But let's move towards actually a negative answer to this question. So let's consider the polyhedral product again. So our S of L and AL. So we know a presentation for AL now. So remember, the generators were just the vertices of L, and the relations were commutators coming from edges. So we can just construct a map from that group to the integers. Let's just send every generator to number 1 in the integers. Okay, this gives us a morphism, and let's look at its kernel. And this will be a group that will denote BBL. So how can we understand this group BBL? So we can think about the classifying space for it. Previously, we had our space S of L, which like in the example of where L was a line, this was a torus. Okay. And so now when we take the kernel of the map to 1, we can actually get a classifying space for BBL. It's just going to be a Z cover of this. So we can think of this as a cylinder. Okay, yeah. So this cylinder will just be a Z cover of the Silvetti complex and its fundamental group BBL. So yeah, let's call this cylinder B of L. We'll come back to it later. Okay, so this is how we got Bestvina-Brady groups. It was no coincidence that the kernel from before, the notation for it was BBL. BBL stands for Bestvina-Brady. Okay, so Bestvina-Brady in '97 resolved this question of distinguishing type FP2 and finally presented groups. Turns out that in general, no, the answer is no. There are groups which are type FP2 but not finally presented. And these gave the first examples. So specifically, they proved that this group BBL is finally presented if and only if L is simply connected. So its fundamental group must be trivial. But BBL is of type FP2 if and only if L is 1 acyclic. So if H1 of L is trivial. So it's first homology with integer coefficients. And so then if we take some appropriate input complex L, which has trivial H1, but not trivial pi1, the theorem tells us that the resulting BBL is going to be of type FP2, but not finally presented. And so one way that we can do that is we can take some flag simplicial complex with a perfect fundamental group. Remember that perfect means it has trivial abelianization. And remember, there's a relationship between pi1 and H1, where H1 is the abelianization of pi1. So if you have some complex L where pi1 is a perfect group, its abelianization will vanish. So I guess we should probably have some examples of these. So we can start with some perfect groups. So the alternating group A5 is perfect. It's a abelianization. It's trivial. And we can take its presentation complex. Now, this might not be a flag complex, but what we can do to make it into a flag complex is we can barycentrically subdivide. Okay, so that gives us one example. Well, this example has torsion. If you want to look for an example without torsion, you can look at the Higman's group. If you haven't seen this before, presentation for this is on 4 generators, and B conjugates A squared, C conjugates B to B squared, and so on cyclically. So D will conjugate C squared, and A will conjugate D A squared. Okay, so we can do the same thing. This group is perfect, so we can barycentrically subdivide a presentation complex for this, and that gives us a suitable complex to put into Bestvina-Brady machinery. Okay, any questions about that? Yeah.
Usually I've heard people say take L to be the 2 skeleton of the Poincare sphere and then take the flag triangulation. Is that the same as what you?
I don't think that's the same, but that also works. Yeah, there's many examples. And I guess these days people have also thought of other ways of constructing groups of type FP2 that are not finally presented that doesn't use this Bestvina-Brady machinery at all. Because really the thing that's working on in the background here is there's a Morse theory argument that it's all okay. So now we come to some more general constructions. So Ian had a brilliant idea that if you study the classifying space for the Bestvina-Brady group of this cylinder here, you can notice that the starting complex SL really only had one vertex. So this is the same vertex. It only had one vertex, but this BBL, it has Z many vertices. So it has vertices that we can assign heights to, which are some integer value. So what we can do with that is we can construct uncountably many more generalized Bestvina-Brady groups by doing a branching construction. Here I attempted to do some Blender 3D models of what's going on in the universal cover, but I don't know how clear that's come out. So let me just draw some more things, make things a bit more apparent. So in this complex S of L, if you look at the single vertex, the link of this vertex will really have something to do with L. So in our case where L was just a single line, S of L was a torus, the universal cover is a plane tiled by lots of squares. And if we look at one vertex and we restrict ourselves to this height function, if we just look up or down, so let's say we just look down, then what we actually see here is we see a copy of L underneath the vertex. So to get the link, we can just intersect with a small sphere centered at the vertex. So it'll be the same case in BL. So BL will just be the quotient of this by the group BBL. So it'll have just one square at each height. So what we can do is, given some cover M to L, which, for example, we can just take M to be the universal cover of L, we can do a branching construction where we do a branched cover of the cylinder BL. And the way that we do the branching is there is some input subset of the integers S, which tells us at which heights we do the branching. And then how do we do the branching is determined by this cover M to L. So in this example here, it's a cover of an octagon, cover of a square by an octagon. And so this will be a twofold cover. And so, for example, if your L was a square, one possible cover this could have is by the octagon. Okay, and then that gives you some big complex. It turns out this is a cat-zero cube complex. And we can just look at the group deck transformations of this branched cover. And so this gives us some group, which we can denote by GL of S. So now as input, we have not just the complex L, but also a subset of the integers S. And this is what allows us to get uncountably many of these groups, because there are uncountably many different subsets of the integers. Okay, and so how are their properties related? So first, we'll need a definition. So we say that a simplicial complex graph retracts if there's a simplicial graph, which is a subgraph of L. And if there's a function we'll call R for retraction from the vertices of the simplicial complex L to the vertices of the graph, such that firstly it has to be fixed on the subgraph itself, but then for every other vertex you either map to something adjacent or to the same thing. So let me draw a little example. If we have some L like this, and if we take the graph gamma, just be this graph here, then whenever you have two adjacent vertices, so these two vertices are adjacent, wherever R maps this vertex, it has to remain adjacent to this vertex. So the map R has to take this vertex either to this vertex or to this vertex. It can't, for example, map it like that. Okay. And so actually one thing that follows from this, if your complex L does graph retract, then it must in particular have a free fundamental group. Because if it doesn't, then just by following through an algebraic topology argument, you see that you get a contradiction. So This does put a restriction on what input complex L you can have, but you can still get quite a few. And something that I proved in my thesis was that if we have an input flag complex L which graph retracts, then given any finite comma M to L, this group GLS of ENs that we construct, this will embed into a RAG. So this is similar to what Agel did, showing that certain hyperbolic groups are virtually special. So we can show that EN's groups are virtually special if and only if the branching set is periodic. So for this certain class of complexes, we can give a specific criterion for when this group embeds into a RAG and when it doesn't. So then using this, we can get a bunch of applications. So this is some joint work with Ian, which was published last year. So firstly, we can construct some exotic small cancellation groups, which are not finally presented, but we can get them to be torsion-free and residually finite, and they embed in finally presented groups, but the word problem is not. So you might think this is surprising, because if you have a finitely presented small cancellation group, then in fact it's hyperbolic and very efficient algorithms exist for solving the word problem. And another thing we can do is we can construct lots of groups which are residually finite but not linear, because we have criteria for when these groups embed into RAGs are linear or not. And so by mixing and matching properties, we can construct groups with exotic flavors. So, for example, this group given here is residually finite, but it's not virtually torsion-free or linear in characteristic 0. And here, another advantage is that every finite subgroup of this group here has order at most 2. So we can fully understand the torsion in this group. Because another way to construct groups which are residually finite but not virtually torsion-free might be to construct torsion groups, such as Grigorchuk's group, for example. But this is not the case here. So this kind of gives some new kinds of examples. Oh, and because we use subsets of integers, we can actually construct uncountably many such groups. So we can actually construct uncountably many groups that are residually finite but not linear.
So this doesn't work if you use an exponent other than 2.
Well, you can use other finite exponents.
Right.
Yeah, you can use finite covers, yeah.
And then the finite subgroup at most 2 statement would involve the P that occurs in the exponent.
Yeah.
Presumably.
Yeah, that's right. Yeah. So we can replace the 2 by any finite group, and then
Right.
any finite subgroup of our infinite group
Right.
will be conjugate to some copy or some copy of a subgroup of the
Right.
finite group that you started with.
Thank you.
And in fact, I think that's all I have to say today. So thank you for listening.